So our next test is going to be on November 3rd. So that's 2 weeks and 2 days from now. And I'll post some study materials tomorrow, and our regular pattern of homework in. So homework due now, and then I'll post another one this evening, which we do in a week. And a couple people requested to look at homework problem number 2. So we're going to do that. And on the idea of back EMF, from near the end last time, the term is used in electric motors and in just inductor coils, but it's used in slightly different ways in those 2 different cases, which is a bit of a confusion that I need to sort out for myself too. So if it's just an inductor coil, there's going to be an EMF that opposes the change in current. So if you apply a potential across an inductor, the current through it starts increasing, but inductors oppose change in current, so there's the potential. That's what lets there be a potential across it, opposing that increasing current. For an electric motor, as it spins, so if you've got your loop of wires in a magnetic field, as it spins, it's going to change how much flux it picks up. If it's completely facing the magnetic field, or it's sliding past it, or it's going through the other way. So that will, the change in magnetic flux will also give you a voltage around that loop. But instead of being from the change in current, it's from an applied magnetic field. And that will oppose the direction the motor is going, or oppose the current through it if it oppose the current which is driving the motor. And number 3 is much easier to make a picture for. So there is just a wire, and we're just going to look at a cross section of it. So there's our wire. And its total radius doesn't really come into account, because for Ampere's law, we only care about how far the enclosed current. So we can make an Amperian loop, which is inside the wire. And just run Ampere's law on it. So B.dl. So the B.dl part is the easier part this time around. It's going to be the magnetic field times 2 pi r. So due to the symmetry and uniform distance from the center, the magnetic field should be the same. And if the current is coming towards us, going around with the right-hand rule. And for the current, it's a little bit trickier. So we just need to integrate the current density over the area. So current density over area. and we need to keep it as an integral because our current density isn't constant. We can't just jump to current density times area because there's greater current near the surface of the wire than there is near the center of the wire. So to turn this into an integral dr, the amount of current that we're going to get in this little dr ring is going to be our area times our current density at that area. So 2 pi r dr. So 2 pi r is our circumference. We're going to give it a dr thickness.
Good.
And the current density at that distance was 3 r amps per meter cubed. This weird unit, when multiplied by r with that hidden meters in it, gives a current density of amps per meter squared, as it normally should. Just convert this from 0 to whatever r we care about. So this ends up being an integral of r squared, and all the other constants can come to the front. So that r squared turns into an r cubed over 3. And I'm going to fix my capitalization. And then we can just divide both sides by 2 pi r. So we just get mu naught r squared, Teslas per meter squared. So most of it just ended up canceling. Okay on this one? All right, cool. That one I'm satisfied with. Number 2, that was a mess. I'll post something which is not a mess.
Will we have something similar to number 2 on the exam?
That one a bit too involved to put on a test. Maybe one of the pieces or the other, but I wouldn't do both in a single problem.
Thank you so much.
A sheet or a wire, sure, but a sheet and a wire together, a little too many, yeah, a little much.
For number 2, I know it might be repetitive to ask, but I was really confused when you started drawing it. Was the XY plane the sheet, were they on stacked on top of each other with the line, or are they technically like in a three? I tried doing like a 3-axis plane when I drew it, and it just didn't work either. I
Uh,
really
my drawings were bad. I'm going to make not good. I'm going to make decidedly better drawings to make clear what I was
okay.
trying to do.
I'll wait
If you
for
didn't
the
understand my drawings, that's understandable. They were bad. I'll make some good ones, but I need to map it out. I won't do it on the fly. I tried. It was bad. All right, cool. Let's move on to our new things. So got inductors. And we looked at what would happen if you just had an inductor and we just applied a constant voltage to it. You get a constant increase in current. Because the voltage across an inductor is proportional to change in current. So if you apply a constant voltage, you'll get a constant change in current, and you'll just get a gradual ramp up in the amount of current. What if there's a resistor in there also? I would make this. An LR circuit. You call it an RL circuit. I guess I'd be okay with that. So if you've got resistors, capacitors, and inductors, 2 or more of them together in a circuit, the kind of circuit is named by what elements are in there. So inductors are measured, their variable is L. So if you've got L and R in a circuit, it's just called an LR circuit. If there's capacitance in there, also it would be an LRC circuit because you've got capacitance, inductance, and resistance. So if you had a circuit that was just this, it would already be running, but if you put in a switch, so it doesn't, start from a high current, what's going to happen when the switch is closed? So at that moment, there's no current. So there's going to be a voltage across the inductor, but not the resistor, because there's no immediate current. So off the bat, no potential across the resistor, but potential across the inductor. And as time goes on, you get more and more current, which means more and more potential across the inductor, which means there's less of the potential, so more and more potential across the resistor, which means there's less left over for the inductor. So the rate of change goes down over time. Mathematically, this actually ends up looking a lot like a circuit with a resistor and a capacitor, or an RC circuit. So this can get its Kirchhoff's loop rule. So just work our way around the loop once that switch is closed. Got our voltage from our battery, which would be our EMF for just V sub 0, minus the potential across our inductor. Which is inductance times the rate of change of current, minus the potential across the resistor, for Ohm's law, needs to add to 0. So this can get rearranged to get everything with current on one side and everything without it on the other side. And just some mathematical tricks, splitting up di and dt and integrating both sides. So integral over the current. Is going to be equal to the integral over time if we multiply both sides by dt. The right side is simple, just turns into T over L. And the left side is similar to a 1 over x integral, but there's some extra bits. So exponentiating both sides and getting that 1 over r factor over. Where we have a very, very similar looking solution to the problem with just a capacitor and a resistor, where this time, instead of building up energy in the charge on the capacitor, we're building up energy in the current through the inductor.
Excuse me real quick. What is the symbol under the T there after the E?
That's our time
Oh,
constant tau,
okay. Thank you.
which this time is our inductance by resistance. So you could also write that as so inductance divided by resistance also works out to have units of seconds if you use Henrys for your inductance and ohms for your resistance. If we switch this around a little bit, so for capacitors, we had our charging equation and our discharging equation. This is going to be kind of like that, where this setup here is ramping up to some value. Paint myself in the corner there. Current time. We've got our exponential decay up towards its final value. And the final value you get is what you'd get if the inductor wasn't there over at all. So you just get your voltage over your resistance. And our characteristic time is over. We can change our setup a little bit. So if there's a resistor and an inductor, and they were being charged or powered by a battery, we're going to make that battery no longer part of the circuit. By just giving an alternate path. The switch is just going to very quickly go from the battery to the other path. So it's like starting with a capacitor charged. Everything that matters is just this. We're going to start with some initial current, and it's going to decay over time. So this is kind of like discharging instead of charging, where energy is going to be lost to the resistor. Where again, our time constant so this in mathematical form looks a lot like the discharging of a capacitor through a resistor. Or whatever your initial current is, it just dies off over time. So some differences for a capacitor. The greater the resistance, the slower it would be to charge something up. It takes more time to flow through a large resistor than a small resistor. A bigger resistor will have a bigger time constant. For LR circuits, the greater the resistance, the faster energy is dissipated out of this circuit, and the shorter the time constant. So if you look at it from an energy perspective, if we have just the resistor and the inductor, we start with energy in the magnetic field due to the current flowing through the inductor. And over time, we get less and less current flowing through it, which means less and less magnetic field, which means less and less energy stored in that magnetic field. And that energy is going to thermal energy in the resistor, because current flowing through the resistor makes it get hotter. So let's work with these a little bit. So first one's kind of plug and chuggy. Just an LLR circuit just like described. So it's going to have its resistor and its inductor. And battery. And a switch. So t equals 0, close the switch. How much current are you going to get in 1/100th of a second? Work it out. So this is going to call for the equation with the increasing current, sort of the analog of the capacitor charging current. Our battery voltage divided by our resistance. Minus e to the minus t. Divided by our time constant. So we've got resistance over our inductance. So this 20 volts divided by 15 ohms gives the long-term behavior of the circuit, where you get 1 1/3 amps at very long times. And I got 1.036 amps. Any questions on this one?
would we ever get just like a tau value, right? That was the time constant.
Sure.
Okay.
I didn't compute it directly, but this one. It's 1/150 seconds. And yeah, you could get that instead of the values of the resistance and the inductance. This one requires a bit of rearranging. And this one starts with the initial current of 2 amps. So there might have been a battery that was removed via switch, but all that matters here is just the inductor and the resistor. So this can use the equation that's much more similar to the discharging capacitor equation. See if you can work it out. How long will it take the current to go down to 1 amp?
Yeah, you can take my car.
So our current equals the initial current. E to the minus t divided by our time constant. So 1 amp. So taking the natural log of both sides. So if we flip something inside of a natural log, that just makes it negative. And then multiply both sides by tau. So our time constant is equal to our inductance divided by our resistance. So plugging it all in, I got about 1.4 microseconds. So if there's a lot of resistance, this can happen very, very quickly, where you don't get persistent current for more than around a millionth of a second. Good on this one. So that's what happens if we have an inductor and a resistor. We've done a resistor and a capacitor. So what about an inductor and a capacitor without resistance? So starting out with a charged capacitor, once this switch gets closed and current flow, conventional current is going to want to flow clockwise, and electrons will actually be going counterclockwise. But the resistor is going to
Did he just disconnect? Oh, he's back. Oh,
He left again.
yeah.
Probably.
Riley, you're
Internet
teaching the
issues.
class now. Let's go.
Well, I don't have any notes, so I guess we're done for the day. I know he's back. Hi, Professor.
indeed, I'm back. Sorry, something, yeah, I disappeared. I returned. So the capacitor is going to have a potential across it, which means by Kirchhoff's loop rule, if there's a potential across one of these, their potential needs to be also across the other one, so we can balance out to zero on the loop. So there will be potential across the inductor, which means current will start flowing. It doesn't start flowing at a great rate immediately because it takes time for current to build up through an inductor. So as time goes on, more and more current flows to the inductor. Eventually, enough current has flowed through the inductor so that the capacitor is now neutral. Enough charge moved capacitor, which means no potential across the capacitor, no potential across the inductor. It doesn't mean the current is going to stop like that. It means there's not going to be any change in current at that moment. So the current's going.
Professor, could you repeat what you said after there being no potential across the capacitor?
Cool. So once the capacitor has had enough charge move through it that its sides are at equal potential, no potential across it, therefore no potential across the inductor, which doesn't mean current stops instantly. It means there's no change in current at that moment because potential across an inductor goes with change in current. So that current that was flowing keeps flowing at least for a little while longer. And it's going to keep flowing, and charge is going to build up the opposite to how it started. Eventually, there's going to be enough charge in the capacitor that the potential across the capacitor slows down the current that's flowing until it stops. When that happens, you're going to start getting a current that flows back in the other direction. So this follows a mathematically different pattern than the previous two. It's going to be charge bouncing back and forth from one plate of the capacitor to the other. A way of seeing why that needs to be is that resistors dissipate energy, but capacitors and inductors don't. They store energy. So there's nothing in the system to make the stored energy go away. So it actually keeps bouncing back and forth between the sides of the capacitor indefinitely.
Behavior that seems to be very similar to a spring or like something with momentum that's on a spring.
The solution is exactly the same as a mass on a spring.
Like Hooke's law?
Yeah. So you can think of the momentum as being related to the inductance, which keeps current flowing the way it used to be going. So that's kind of filling the role of mass in this electronic oscillator. And the capacitor holds the role of the spring, because if things flow too far one way or the other way, it tends to push things back. So unfortunately, the one that has a picture that looks just like a spring is doing the job of the mass, and the one that looks nothing like a spring is doing the job of the spring. So yeah, very different physical system, but because you've got something that has inertial-like properties and something that has restoring to equilibrium forces like a spring would, being the capacitor, you get the same mathematical solution. So Kirchhoff's loop rule, our potential across our capacitor plus our potential, potential across the inductor plus the capacitor sum to 0. Looks like 2 two entirely separate variables, but current is the rate of change of charge. So the rate of change of current is the second derivative of charge. Yeah, I mean, part of the reason that we do springs in 195, wait, no, 230, yes, is a lot of things are mathematically similar. It's a very useful model. So same mathematical solving trick, sines and cosines. So the charge that you're going to get across the capacitor at any given time is going to be proportional to the starting charge. You don't start with any charge. It's not going to build up from nothingness. You start with no energy in either stored in the capacitor or the inductor. Cosine of omega t, where omega is our angular frequency, plus our phase shift phi. So this is just taking into account for the fact that maybe we didn't start like this. Maybe we started with current in the inductor, but no charge in the capacitor, or some combination. This is just going to shift the phase of our cosine curve to match our starting conditions. And our angular frequency, which is 2 pi times the frequency, is 1 over the square root of the inductance times the capacitance. So if there's a very, very large inductance, the current persists longer. And if there's a very, very large capacitance, it takes longer to build up a significant potential across the capacitor. So both a high inductance and a high capacitance tend to slow down the oscillations. For the current, which is just the rate of change of our charge stored up, taking the derivative of our charge equation, so again, sinusoidal. In this case, Q0 and I0 are not necessarily initial current and initial charge, but rather maximal current and maximum charge. Because you could start with 0 current, but just charge on the capacitors, and eventually you would get some current. Or 0 charge on the capacitors, but just some current, which would lead to some charge being built up on the capacitor plate.
Wouldn't it be negative I naught, or are we just ignoring that?
Oh,
Derivative of cosine is negative sine.
my bad. So the solution is correct. The steps I took to get you there were wrong. Because the current should be minus dq over dt, which is a bit unexpected, but it's what lets the math work out. So if we have our positive current going around that way, current going in that direction is actually going to reduce the charge stored in the capacitor. So if current is defined as going around in that direction, then the current is actually minus the rate of change of charge, which lets us get here. Drop that. Your calculus is correct.
Is that the same? Like, I feel like before, didn't we just say that I was dq dt when we were doing RC circuits? Or did we also say that when we were doing RC circuits?
For I think we just said it as uh, I'm not sure. I don't think we use this sign convention in RC circuits. I think it's just for this we use that sign convention. You can use opposite. It can be dealt with either way, but then you just, the minus sign will pop in either in your definition or how you set up your change in voltage across the capacitor.
Okay.
Cool. So we, yeah, used a different convention for that. Thank you for checking. So for just getting some sines and cosines because they're just so pretty. Our charge will go like that, and our current will go like that. We're halfway through a period. The current is 0 again, but the charge has flipped. And the current starts flowing opposite direction to bring the charge back to how it used to be. So something pretty cool is what the energy does. So there's no resistor. So energy should be conserved. There's nothing dissipating energy from the system. So the energy in the electric field, or the energy stored by the capacitor, is 1/2 charge squared over capacitance. And the energy stored in the magnetic field, or stored by the inductor, is 1/2 inductance times current squared. So instead of just using charge, we can put in the equation for it. And for magnetic field, we put in the equation for energy stored in an inductor. And the equation for the current. We've got Q naught omega for our I naught. And our total energy then must be the sum of these two things. So U is standing for our energy or potential energy. So UE is energy in our electric field. UB is energy in our magnetic field. Where the electric field is what the capacitor has, and the magnetic field is what the inductor has. So remember, our angular frequency omega was equal to the square root of 1 over LC. So omega squared 1 over LC. And we've got L times 1 over L. So these two terms can actually come together. This is Q squared over twice the capacitance times the cosine. This is Q squared over twice the capacitance times the sine squared. And that's just cool. Energy is indeed conserved. So time drops out of the total energy stored equation. So if you look at the energy over time, It's a super boring graph. But if you look at the electric field energy, and the magnetic field energy, so wherever the current is biggest, that's when there's no charge on the capacitor. So all of the energy in the magnetic field. And whenever there is no current, that's when the charge on the capacitor is greatest. And there's all the energy in the electric field. So this is similar to a mass on a spring. The mass is going fastest when it's in the middle and the spring is in its equilibrium position. And there's the most energy in the spring when the mass is still.
Professor, which ones are which? Sorry for the colors.
Fair enough. If it doesn't actually matter, but if our phase shift is 0, then we're going to start with our energy stored on the capacitor. So it would be like that. But with a different phase shift, it would be the other way around.
All right.
And it's worth pointing out something pretty neat about the period on this graph. So we start with all of our energy on our capacitor. We have all of our energy on our capacitor again. So this looks like one complete period, but it's not. All the energy is on the capacitor again when the charges have flipped, and now the side that used to be positive is now at its maximal negative charge. This is actually period over 2. And that's the full period. So the magnetic field energy is maximized 1/4 the way through the period and 3/4 the way through the period. And let's work with circuits that have inductors and capacitors. So you know the period. What must the inductance be? Is your hold on your periodic, rusty with your periodic motion equations. Angular frequency is equal to frequency, and our period is 1 over the frequency. So frequency and angular frequency will both be measured in inverse seconds, and period could be measured in seconds. This is mostly just manipulating the equations. So our angular frequency is going to be equal to the square root of 1 over LC. Which is also equal to 2 pi times our frequency, or 2 pi 1 over the period. That's a very symmetric looking fraction. Neat. So squaring both sides. And we want the inductance, so we need to isolate for that. So I'm just plugging in 1 second and 0.4 farads. I got 0.0633 Henrys. Good on this. So let's look at an energy problem with an LC circuit. So there is 0.05 joules in this LC circuit. So some of it can be in the inductor, some of it can be the capacitor, and how they share it changes over time. So what will be the maximum current and maximum charge given the amount of energy there? So the hint is for the maximal current, all of the energy will be in magnetic field. So you'll have 0.05 joules stored by the inductor. And for the maximal charge, all of the energy is stored in the capacitor. So you have 0.05 joules on that capacitor. So if all of the energy is on the capacitor, then our energy in the capacitor will be 0.05 joules. So multiplying both sides by 2 times the capacitance. So 0.1, and our capacitance is 0.5 farads. And for this, I got 0.222. And for the inductance, it's maximized. So solving for I, need to multiply both sides by 2, divide both sides by the inductance. Square root both sides. And for this, I got 0.707 ohms, or root 2 ohms, or 1 over root 2 ohms. Questions on how this one goes? So let's move to the only place we could be going. We did every pair on their own. What if we've got an inductor, a resistor, and a capacitor? So this is an LRC circuit. Switch. We have our capacitor. And our resistor. So we start with some charge on the capacitor. Once the switch is closed, we wouldn't get current flowing immediately because the inductor would resist the change in current. Q squared is 0.05 joules. The units don't match up in your equation, but the rest of it should be fine. Oh, did I drop as so over time, you're going to get more current because current's being driven by the potential across the capacitor. As current increases, you're going to start getting potential across the resistor. So when the capacitor is fully discharged, there will be a potential across the resistor still. So there's going to be some loss of current through the inductor. So if the resistance is small enough in a circuit like this, it ends up looking a lot like what we had without a resistor, but just some energy lost over time. If the resistance is very, very big, it looks a lot like just an exponential decay. So our Kirchhoff loop potential across inductor, potential across resistor, potential across capacitor, sums to 0. And these all can be written in terms of the charge or time derivatives of the charge, including second time derivative of the charge. So if we use our negative time derivative, for our positive current, we get a differential equation. Woo. It has the same form that you would get for a damped harmonic oscillator. So a harmonic oscillator, a mass on a spring, going through some sort of viscous fluid. There's some energy dissipation in the system. The solutions are not the simplest. There are a few important cases. If it's similar mostly to the capacitor and inductor system on their own, and the resistors changing it, but not severely, or if the resistance squared is less than 4 times the inductance divided by the capacitance. So if the resistance is small enough, then it still will follow a cosine-like curve, but the resistor in there is going to put in an exponential decay term. So our exponential decay term is there. So more complicated. Big picture, what this is doing is we've got a cosine multiplied by a decaying exponential. So that decaying exponential puts an envelope, if you will. It sets a maximal value for what this function can be. And the cosine just oscillates within that envelope. So an oscillation that just gets smaller over time. This has a omega prime in it. Yeah, sine wave, exponentially decaying magnitude. Yeah, cosine wave, exponentially decaying magnitude is how it was written, but yes. That's just a phase shift different, which there's a phase shift in here. Yeah. So you look at this as the magnitude of that sine or cosine wave, it exponentially decays over time. Absolutely. Would the resistor give off pulses of heat or steady heat? Interesting question. The energy usage of the resistor goes as the square of the current through it. So there are moments when there is no current, when the things are turning around. So there's no current when dq over dt is 0. So there would be no energy taken by the resistor at that moment. Whether it gives off of pulses of heat or steady heat kind of depends on the thermal properties of the resistor, because it's very possible that the time scale for it to release its heat into its surroundings is substantially longer than the period of oscillation of this circuit. So it would get warmer in bursts, but as long as it's warm, it's still going to be radiating that heat off into its environment. So it's possible that if you had a period which was long enough and a resistor that dissipated heat quickly enough, it would be pulses of heat that it releases. It's going to take energy in pulses either way, though. So if it's capable of still doing this oscillation, it's known as underdamped. Where dampening is the dissipation of energy. So this is when we have got R squared less than this critical value determined by the inductance and capacitance. The one oddness in this equation, which I absolutely should have mentioned, but have not yet, is there's actually a change in frequency. So this prime by the omega doesn't mean take the time derivative of our frequency. It just means different version of it. Like sometimes prime meant before and after. Small l. Oh, that's just a t that I forgot to cross. There, that's clear. So yeah, the exponential is time dependent and the oscillation is time dependent. This omega prime term just means omega, but different. So our original frequency without any resistance was just 1 over LC. It's changed to this new frequency, or new angular frequency. So this solution clearly breaks down when this term is bigger than the first term, because then we'll be taking the square root of a negative. And then we get an imaginary frequency, and it's weird. So this is going to be positive so long as our resistance is less than the square root of 4L divided by the capacitance. And that is the underdamped case. If they are equal, that is critically damped. And that does allow it to cross zero at most once. It's critically damped, you don't get oscillations anymore. Something kind of more like that. And it can be even more, which is called overdamped. And that qualitatively looks a lot like critically damped. There are differences, but in both cases, there's just too much resistance to oscillate at all. Not going to go for the mathematical form of those solutions. There's already enough here. So what the resistance does changes the frequency of it to something which is slower. And eventually our solution breaks down for what our new frequency would be. And then it just doesn't exhibit oscillations anymore. It's just more exponential decay-like. And what determines that is how big the resistor is compared to the ratio of the inductance over the capacitance. This one mathematically kind of ugly, but more realistic, because it's really, really hard to make a circuit that has absolutely no resistance in it. So if you make an LC circuit, you probably actually made an RLC circuit or an LRC circuit, because there's probably some resistance in there, and it's not going to oscillate back and forth forever without dissipating energy. Usually you just lose some things to heat eventually. Questions on what happens when the resistor gets thrown in? It's definitely the most complicated case of them all, which is unsurprising because it's the most complicated setup. We got all three of them. Right. Let's work with it a little bit. So we've got a resistor, we've got an inductor, we've got a capacitor. So this is just going to be those elements in a simple loop. Uh, so the angular frequency would be given by the omega prime equation. We need to take into account how the resistor changes the frequency. And then without it, you just use the equation for an LC circuit. So little plug and chuggy. So plug and chug. So without the resistor, Henry's times 0.0012 farads, and that is 91.3 inverse seconds. So we just need to add in a little bit extra for our resistor. got our resistance squared. Or 4 times our inductance squared. And working this out, I got 52.04. I just can't stop writing. So the oscillation gets slower. The frequency goes down with the addition of a resistor. Good on this. All right. One more. If you wanted it to be critically damped and you already had a 30 millihenry inductor and a 5 millifarad capacitor, what resistance would you need? So the equation for being critically damped is that the resistance squared must be equal to 4 times inductance over the capacitance. So resistance is just the square root of 4 times the inductance divided by the capacitance. And it would be best to convert into base units just to show, but the factors of 1,000 will end up canceling each other out. But it's just good practice. It's actually 0.03 henries at 0.005 farads. And this works out to be just under 5 ohms. Good on this one. Radians per second. Yeah, but radians are the most ignorable unit. Because if you multiply it by 2 pi, you get frequency, which is just inverse seconds. So yeah, 2 pi times that angular frequency is just how many times it happens per second. this will be our stopping point unless anyone has any questions. Next time, we're going to see what happens if we take these circuit elements and instead of attaching them to a battery, we drive them with an alternating current source. So the applied voltage will be following a sine or a cosine wave.